Assalamu alaikum. Can you all hear me? Okay, great. So just give me a minute and we'll start. Okay, so is the screen visible to everyone?
Yes.
Okay, so let's start. So we'll be covering the chapter of waves and some questions from superposition as well. So that'll be the topic for today, and the question would be obviously some like key questions that uh, the type of questions or the concept behind them. You need to have a good idea about a good understanding about them, so you can solve similar questions in the exam. Okay, so start. Sound waves are longitudinal waves. By reference to the direction of propagation of energy, state what is meant by a longitudinal wave. Obviously, this is like O-level basics. So by reference to the direction of propagation of energy, the direction of propagation of energy in a longitudinal wave is parallel to the direction of oscillation. So this would be my oscillation, or the motion of molecules, and this would be the propagation. So both these directions are parallel to each other. So this is something simple. Stationary sound wave in air has amplitude A. In an experiment, a detector is used to determine A square. The variation of A square with distance x along the wave is shown in figure 4.1. State the phase difference between the vibrations of an air particle at x equals 25 centimeters and the vibration of an air particle at x equals 50 centimeters. So particle at x equals 25 centimeters would be a particle somewhere here, I think, yeah, this particle. And a particle at 50 centimeters would be this. So what would be the phase difference? Anyone?
360.
Yes. The proper answer would be 360, but 360 is obviously the same as 0. So you could write 0 as well. And now another question. What's the difference between path difference and phase difference? How are the two terms different?
In terms
Or
of
what?
एंगल हो तो फेज डिफरेंस होता है, और अगर in terms of distance वैसे ही हो तो पाथ डिफरेंस.
Yes. Phase difference is in terms of angle. So you could either write it as 2 pi, 0, or whatever. And if I'm talking about the path difference would be the distance. And the distance is usually written in terms of wavelengths. So the path difference between these two waves, if that was the question, I would have said 1 lambda. One wavelength would be the path difference. No, Umar is asking why won't the phase difference be 180? The reason is because both these points are on different waves. So the phase difference is 360. This this green point, this green line would have a 180 phase difference with either of these black red lines, because that's part of the same wave. This is clear. Like this was something like one of the basics. The amplitude squared, so one of the peaks would be a trough, and no, that's not the case. The amplitude was squared. What this told me is that there was no negative value. If you see, it's everything is above zero. So everything is above zero because of this. Still, the max value would be at the point where the maximum value was being squared, and the minimum value would be where the minimum value was being squared. So still, a crest is at a crest, and a trough is at a trough. So that's something that would remain the same. The speed of the sound in the air is 330 meter per second. I hope this is clear, Umar. If not, then do write down your query. The speed of the sound in air is 330 meter per second. Determine the frequency of the sound wave. Obviously, I need to find the frequency of the sound wave, and they've told me the speed. So the formula for this, I do know that v equals f lambda. So I know the speed. What's the other property that I can find? They're asking me to find the frequency. Can I find the frequency directly from the graph, or do I need to find the wavelength in some way and then find the frequency? What do you guys think? Okay, so Omar is asking how would we differentiate between crest and troughs from this graph? They would just be how they are on any random wave. So the crest is still a crest and the trough is still a trough. The crest is the maximum amplitude, point with the maximum amplitude, and a trough is the point with the minimum amplitude. So in a normal wave, there are often times where the amplitude goes negative at the crest or at the trough. So this could be A and this could be negative A. So although that is still there, but the absolute values never reach negative. That's just uh, a binary difference. Like they they cannot be a negative value here right now because the value is being squared. That's the only difference we get. The crest remains where crest are and the troughs remain where the trough are. The point is the same. The value increases. The value for the crest increases and so for the trough. There is no time given, so we need to find the lambda. Yeah, you're right. And somebody raised a hand. So his hand is down. Yeah, so we need to find lambda. So how do we find lambda? We know that these 2 points are at a phase difference of 360 degrees, or as I mentioned, their path difference is 1 lambda. So what is the difference? It's 25 centimeters. 25 centimeters equals 1 lambda. So this is, I know, this is something I know. Now I know the speed, it's equal to 330, and I know lambda, it is equal to 25 divided by 100. So can I find the frequency from this? Frequency would be equal to speed over lambda, 330 divided by 0.25, and the answer would be, I think, 1320. Let me check. 1320. So the frequency would come out to be 1320 hertz. So that would be the frequency. Now the next part, determine the ratio amplitude A of the wave at x equals 20 centimeters, amplitude A of the wave at x equals 25 centimeters. So this is where, Umer, your confusion, I think, comes into play. Like, this is the part where the difference comes because of this A being squared. This is where the difference comes. Okay, so I need to find the ratio. So let's just call this ratio alpha. So alpha equals amplitude of wave at 20 and the amplitude of wave at 25. So the what's the amplitude of wave right now from this graph? Just this is 4 and this point is 2.5, 2.6. This is 2.6. Okay, so I need to find this, but the values I'm able to find are, I can only find a2 square and I can only find a25 square, like the amplitude at the value of 25 squared. I can't find the exact amplitude. I can only find the square of it because these values are in square. So I just go on with this. Now what I do is, if I make a ratio from these two values, it would come out as a20 divided by 825. Both these values would be squared, and I could similarly write them as a20 divided by a25, this whole thing squared. So this is how I can go. And if a was equal to this, the ratio that I need to find was equal to this, I could simply write this as equal to square. Similarly, I could also say a equals, or the alpha, or this alpha equals, I'm now using this equation stuff. So alpha equals under root a to the power 20 whole square divided by a to the power 25 whole square. Is this clear to everyone how I came to this part? Is this part clear? So I'll assume it is there. So someone's saying, repeat please. Okay, so the values in the graph were not were not the amplitude, rather they were the square of the amplitude. 2.6 divided by 4 तो होगा, लेकिन under root भी होगा. Okay, so these values were a square, not a. What I need to find is this ratio. I need to find the ratio which I just called alpha, which is equal to a20 divided by a25. Amplitude at 20 centimeters divided by the amplitude at 25 centimeters. But the problem is I can't find the amplitude at 20 centimeters. Or let's just do it a simple way. What I'm finding is, from the graph, I have two values. I'm able to find two values from the graph. One is this, which is a 20 whole square. And then there's this value, which is a 25 whole square. So I have these two values which I'm getting from the graph. Now I don't need these values. I don't need the square of the amplitudes. I just need the amplitudes. So what I do is I use these values and I underroot them. So obviously a20 would be equal to under root a square the amplitude at 20, right? So that's what I do. So I go with this and I find my ratio. So my ratio would come out as equal to 2.6, which is this value, 2.6 under root divided by under root 4. So this would obviously be 2.6 divided by 4. So this is all I was doing. I was just mathematically proving why would that be the case. So if that's a bit confusing, I hope this part is clear to everyone. 2.6 divided by 4 under root, because all these values were the square of amplitude. So with this, I'll get the amplitude as being equal to under root 2.4, 2.6 divided by 4. So yeah, the ratio comes out as 0.81. So this would be my answer. I hope this part is clear to everyone. Okay, the next part, state what is meant by the frequency of a progressive wave. So obviously the frequency of a progressive wave is the waves produced per unit time. So that's what frequency actually is. The number of waves produced, the number of oscillations of a point per unit time. Right. The thing with O level and AS, some things are different. Was some concepts we go a bit advanced in them. So one of them is frequency. So previously in O levels, frequency was the number of waves produced per unit time. Now in AS, the thing we need to answer them in a bit detail. The number of oscillations by a particle or the number of oscillations per unit time. So the number of oscillations would give you 1 mark, per unit time would give you the second mark. So this is how this is supposed to be done. And now the other two, this question and then the next part are regarding Doppler's effect. So I will just revise it a little bit with you guys. So what Doppler's effect actually is. So we have some terms with us which are involved: F naught, Fs, Vs, and V. So F naught is the observed frequency, which a person would observe or what is observed. Fs is the frequency of the source. The frequency of the source is what is producing the wave, like a speaker or a horn, whatever it was, whatever is the source of the wave, that's the source, and the frequency of that, this frequency with which the actual sound is being produced, that's the frequency of source. And then there's this velocity of source, which is the velocity with which the source is traveling, the speaker or the horn or whatever it is, it's moving. And then V is the velocity of the wave, which is the velocity of the wave in the medium. So for example, if it's light wave, then it's 3 times 10 to the power 8. Or if it's sound waves, the speed of sound in air is 330 meter per second. So this is just a recall. And then we have this formula for these two formulas of the Doppler effect. One is for the frequency, the other one is for the wavelength. And obviously, there's like this plus minus thing involved. So sometimes it would be a plus, and at other times it would be a minus. So when do we go for a minus sign? We go for a minus sign when it's an approaching source, meaning it's moving towards the observer. And when do we move away from the source? When do we use a positive sign? We use a positive sign when it's a receding source, meaning it's moving away from the observer, like it's going away. So that's where we use this. So this is something like keep this in mind. And similarly, lambda naught is the observed wavelength, like the wavelength a stationary observer would observe due to this motion. And the idea is when the source or the speaker which is producing the sound moves, so the frequency which is observed by a person who's stationary, who's not moving along with the source, the frequency he observes or the wavelength he observes is a bit different. So how different it is or what's the value of it, that is what we calculate through this formula. Okay, so now cathode ray oscilloscope is used to determine the frequency of sound emitted by loudspeaker. The trace produced on the screen of the CRO is shown in figure 4.1. The time-based setting of the CRO is 250 milliseconds per centimeter. So that the frequency of the sound wave is 1600 hertz. So obviously we'll like again mark this point, and similarly I could mark this point as well, and then I'll calculate the number of boxes between these points. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. They're coming out, I think, around 13 boxes, if I've not made any errors. So we have 13 boxes. I know the time-based settings, which is 250 times 250 milliseconds, microseconds. So the unit for microseconds are 10 to the power -6. So obviously this would give me the time period. And to find the frequency, so the frequency is equal to 1 over time period. So I do a 1 over it. So I inverse this value and then I'll get the answer. So 15 times 250. Sorry, it's not, I don't know how I made this mistake. It's not 13. Uh, there were 13 boxes, 13 small boxes. So this was equal to 2.6 centimeters, I think. Yes. So obviously, nonetheless, you could just use the scale with you and you could find it and you'll get the answer for this part. 1 over 2.6 times. This time it's giving me a closer value. Okay, so we just show how it's equal to 1600 ohms. Okay, so the 1600 hertz. Okay, so now the actual part comes in. Loudspeaker in B emits a sound in all directions. Person attaches the loudspeaker to a string and then swings the loudspeaker at a constant speed in a horizontal circuit above his head. An observer standing a large distance away from the loudspeaker hears sound of maximum frequency 1640 Hz. The speed of sound in air is 330 meter per second. Determine the speed of the loudspeaker. So if I, obviously I need to determine the speed of the loudspeaker and I know the frequencies. So if I now use this formula and see what values do I know. So I need to determine the speed of the sound speaker and the observed frequency. They've told me that the person standing hears a frequency of 1640 hertz. So F naught equals 1640 hertz. So this is something I already know about F naught. And then there's the speed of the person, the speed of the loudspeaker, which I don't know. I know the speed of the source, or frequency of the source, which I just found out, showed in the previous part that it's equal to 1600 hertz, because that's the same speaker when we which we were which we are using. So it's 1600 hertz. Then the next part would be Vs, which is the velocity of the source. So the velocity of the source, obviously we don't know this. So that's what we need to find. And then there's the velocity of this wave, which is 330 meter per second. So I have this with me, and I just need to use this to find the value and to find the answer. So obviously, now the only catch right now here is, what do I do with the sign? Is it supposed to be a positive sign or the negative sign? And even if you look at the question, the person attached the loudspeaker to a string. And if this is the person standing and this is the loudspeaker oscillating in a circle, and maybe just let me draw it somewhere else. Okay, but I can't tell it, like obviously I will obviously have to reduce it, but the problem right now, I'll just highlight it for others as well. This is the person and he's rotating the loudspeaker in a circle. So there's a point at which the loudspeaker is like moving away from the person. Like the loudspeaker might be moving in this direction, and then the loudspeaker might be moving towards me. And let's say this person who's stationary, who's observing the source. So there are instances when the loudspeaker is coming towards the person, and then there are instances when the loudspeaker is moving away from the person. So now, how do we determine the sign? So the sign, determining the sign could be some simple observation, and that would be that I know I know that the observed frequency, I know the value of observed frequency, it's 1640. And I know the frequency of the source, which is equal to 1600. Now, the question is V over V plus minus Vs. Is this whole thing supposed to have a value greater than 1 or lesser than 1? This is being multiplied with 1600, this whole thing is being multiplied by 1600 and giving me an answer which is equal to 1640 hertz. So is this value being multiplied, is this 1600 being multiplied a value greater than 1 or a value lesser than 1? So obviously by simple observation I can tell it's being multiplied with a value which is greater than 1. So the value is supposed to be greater than 1. And how can I get a value for this to be greater than 1? So that is only possible when the sign is negative. When the denominator is greater than the numerator. So yeah, when the denominator is greater than the numerator. Sorry, to get a value greater than 1, the denominator must be smaller than the numerator. Why so? For example, if I need a value greater than 1 and if I have 5, there should be something less than 5 beneath it. So the denominator must have a greater value than the numerator, and only then would this give me a value of 1 or greater than 1. So this is supposed to happen, and that's how I know there should be a negative sign. And obviously a negative sign is for an approaching source. So I know that the maximum sound that he hears is only when the sound is coming towards him. So I hope this part is clear to everyone. If it's not, then like, just feel free to ask. I'll be more than happy to explain it again. So that's how we get to know that the sign is supposed to be negative. And that's what we use. We now know everything in the formula. So I'll just use these terms. 1640 equals 1600 times 330 divided by 330 minus x. So obviously you could use this formula and find x again. Okay, so someone is asking me to do it again. So I'll just explain it again. How I determined that the sign must be negative. Okay, so if I simply look at this formula, if I simply look at the formula, I'll get to know that f naught, my answer, I could also write it alternatively as like something is this times fs. So I know v. So I know 1600 is being multiplied with a value and giving me an answer greater than 1640. So obviously this whole thing is supposed to be greater than 1. And how would it be greater than 1? It's only possible when I have a negative sign beneath this. So that's what I was explaining, why there should be a negative sign, because the denominator must be greater than the numerator. So that's the whole explanation. Or in other words, if you don't like this theory, so you could also memorize that when there's an approaching source, the frequency is maximum. And when there's a receding source, the frequency is minimum. So that's another way. Maybe you can memorize this if you don't like the theory or you find the reasoning a bit complicated. So this would be the answer, that the frequency is minimum when it's a receding source, and the frequency is maximum when it's an approaching source. So, and obviously for an approaching source, the sign is negative. So that's why we use a negative sign. And I'm left with this formula, and I'm leaving it to you guys, and you can solve it and find x. So, Eamon, I hope this part was clear to you. If not, then feel free to tell me which part's not clear. Okay, so till then, I'll move on. Okay, so they're now asking me about the Doppler effect. Okay, so there's this standard definition for Doppler effect, which I'm writing it down, and you can use it in your exam and you'll get your marks. So Doppler effect is a phenomena where the observed frequency of the wave is different to its source frequency due to the movement of the source relative to the observer. So like memorize this definition and it'll get you the 1 mark, or even if it's a 2 mark definition, you'll get both marks. So I actually made this definition from the mark machine. Okay, so a car travels with a constant frequency along a straight road. The car horn with a frequency of 400 hertz is sounded continuously. A stationary observer on the roadside hears the sound from the horn at a frequency of 360 hertz. The speed of sound is 340 meter per second. They're asking me to determine the magnitude, v, and the direction of the frequency of the car relative to the observer. So the direction, whether it's a receding source or a preceding source, like it's approaching source or a receding source, and the magnitude of v as well. So it's the same thing, same stuff they asked me in the previous question. as well. But right now they're also emphasizing on the direction as well. So again, what do I do now? I first write down the stuff I know. Okay, so I first write down the stuff I know. So F naught, the observed frequency. Do I know the observed frequency? Yes. The stationary observer hears the sound from a horn at a frequency of 360 hertz. So I do know the observed frequency. It's equal to 360 hertz. That's what it's equal to. Do you know the frequency of the horn? Yes. They've told me it's 400 hertz. So I know that as well. Now, what else do I know? Do I know the velocity of the source? Uh, the car travels at the constant velocity. No, I don't know this. Yeah, I don't know the velocity of the car. So I'll write a question mark with it. And then there's the velocity of the wave, which I know, which of the sound wave, which I know is equal to 330 meter per second. So this is all the stuff I know. Now, the formula was F naught equals Fs times V divided by V minus Vs. So this was my formula with me. Now, what I do is obviously I look at the theory stuff. So I'll get the minimum frequency when it's a receding source, and I am getting a minimum frequency. So the source frequency, the minimum frequency, or a better way to like write this, yeah, this is I think enough. So the frequency is minimum. The frequency of the source was 400 hertz, and the observed frequency was coming out to be less than that. So obviously this would be a receding source and the sign would be plus. So that's something I know. All right, my mistake, I should have written plus minus. So yeah, so it's a plus. What's the year of this past paper? Sorry, I don't have the year of this past paper. For some reason it got cut from the paper, like the page that I printed on OneNote, it's not there. Okay, so but what do I know is that it would be a receding source because the frequency is minimum, like it's less than the observed, less than the frequency of the source. So I just write the values. I use a plus sign and I write the values. So F naught would be 360 equals 400 times 330 divided by V. V would be 330 plus Vs. So from this, I could find Vs. And since I know it's a receding source, so I could say the direction would be moving away. And you all could like use this formula and do the calculations and get the answer. I'll leave that up to you guys. Okay, so the next question would be regarding these deflection gratings. So this is the formula which I have written for you guys. So we have this formula, and red light of wavelength 640 nanometers is incident normally on a diffraction grating having a line spacing of 1.7 times 10 to the power negative 6 meters. Negative 6 meter as shown in figure 6.1. The second order diffraction maximum of light is at an angle theta to the direction of the incident light. So that the angle is theta. So I need to show that the angle of the second order is theta. So just a second, by the way. Okay, so I'll come to the formula, and there are some stuff involved in the formula d, n, lambda, and theta. Theta is something that I'm supposed to find, and lambda they've given me 640 nanometer, and n they've told me that it's the second order, and d they've given me the line spacing, it's 1.7 times 10 to the power negative 6. And sometimes they won't give you d, they would tell you how many lines are there per like the total number of lines there per meter cube. So you'll have to, sometimes you'll have to inverse the whole thing and then find the spacing. So sometimes they would just tell you the density, like 1,000 spacings per meter. So you'll have to find the spacing yourself. I know this stuff. and I just use the formula sine theta equals n lambda over t. So it's 2 times 640 times 10 to the power negative 9 divided by 1.7 times 10 to the power negative 6, and that's sine theta. So I'll invert sine, and obviously I could show that the angle is equal to 49 degrees. So that's what I just do. Now, the next part is determine a different wavelength of visible light that would also produce a diffraction maximum at an angle of 49 degrees. So I need to show that there's also another wavelength in the visible light spectrum, which would give me another diffraction maximum at an angle of 49. So the thing would be that the order could be different, but what matters is that the answer is that there would be a maximum at 49 degrees. It could be the first order maximum, second order, third order, fourth order, or any such order. But what it should do is it should give me an angle of 49 degrees. So how do I do this? Is I first this is something you all need to know. You all need to know the range of visible light. So this is something you're all supposed to know. The range of visible light lies in this region, 380 nanometers to 700 nanometers. So this is where this whole range lies. And this is red and this is violet. So this is violet. So this is my range for the visible light. Now what do I do is I backtrack the formula. I know for the formula I know that uh, d sine theta equals n lambda. I know this formula. What do I do is that I make this part the subject, d sine theta divided by n. I equate it with lambda. This is the equation that I make, and the stuff I do next is I give the value of d, which is 1.7 times 10 to the power negative 6, and sine theta they've given me that the angle should be 49 degrees. So it's sine 49 divided by n equals lambda. Now, what do I do is I know that the value of n was 2 at wavelength of, okay, so just a second, I'll use different color codes to explain this better. Okay, so what do I know is when I divided this with the value of 2, the wavelength was supposed to be 640 times 10 to the power negative 9. So this is something which I do know. Now what do I do is I apply different values of n. So for example 1 and for example 3. So if it was giving me a value of 640 when n was 2, so what would be the values when n would be like when I would change the value of n? So I just do this through my calculator like a trial and error stuff. So 1.7 times 10 to the power negative 6 times sine 49 divided by 1. So when n is 1, I get a value which is equal to, I think, 1283 nanometers. 1283 times 10 to the power negative 9. And when n is 3, I just use my calculator for this. And when n is 3, I get a value of 427 times 10 to the power negative 9. So these are the values I get. And I get this by giving a value of 3, by dividing this with the value of this, and by a value of this. So what was supposed to be here was n, and what was supposed to be here the wavelength. So what I do is by like varying the values of n, I get different values of wavelength. Now what I do is I just like simply observe 640 was in the visible spectrum, which was coming out for a which is coming for a value of n equals 2. Now n equals 1 gave me a value of 1283 nanometers, which is out of the visible light region. So it's out, so I don't like, I just ignore the value. The next thing, 427. That's part of the visible light spectrum. So that's what I use, and that would be my answer. And that's why I write 427 nanometer. So is this part clear to everyone? Like this is one of the tricky questions in this whole stuff. So is this clear to everyone? Okay. Anyone else? So Eamon's good with it. And what about the rest? Okay, so the next question is interference fringes may be observed using a light emitting laser, which is a light emitting laser to illuminate a double slit. The double slits act as two sources of light. Explain the part played by diffraction in the production of the fringes. So how do the fringes, and this is about like the normal grating stuff, double slit experiment. So the part played by the fringes, the part played by diffraction in the production of fringes. How does diffraction of light, which happens here, causes diffraction? How does the diffraction of this light causes diffraction? Okay, so the answer to this could be summarized as this: due to diffraction. I don't know what happened to the screen. Yeah, so the answer could be that due to diffraction, the waves split and spread. The waves spread at the slit. So diffraction is the reason why waves spread when they enter the slit. Then what happens is once they've spread across, when they've spread in all directions, they meet at some common points on the screen. They meet at some common point on the screen, and they meet and overlap to form fringes. So that's how deflection helps in the production of fringes. Because if there was no deflection, the waves wouldn't have spread in all directions. They would have met at common ends and common points and overlapped, and not neither they would have produced any fringes. So this is the answer. You could just write it down somewhere or like keep this in mind. So if a question comes and they ask you how did deflection produce these images, this is how you answer it. And the next part is the reason why a double slit is used rather than two separate sources of light. So why do we use two double slit rather than two sources of light? Rather than two separate sources of light. So can anyone tell me why? Like why are we using the same laser and having it pass through two slits, then rather than just use two different sources of light? So the reason for this is we need coherent waves which are the same uh, phase difference and have the same frequency. So that's very hard to achieve when the sources of light are different, and it's very easy to like you don't need to do anything when the light source is the same. So we need to keep the light source the same, and for that we need to use double slits. So that would be the answer to this. Yeah, that could be the answer. So someone just messaged me some answer. Yeah, that is a possible answer, but that's not necessary. That's like something very hard to achieve. So, like if we use two different sources, coherent waves, that's something like almost impossible to achieve. So that's why there would be some errors. So we just eliminate the whole stuff and we just used coherent waves, the same source of light, and we pass it through two double slits. Okay, so the next part is an interference pattern is observed on the screen AB. The separation of the slits is 0.48 millimeters. The slits are 2.4 millimeter from AB. The distance on the screen across 16 inches is 36 as illustrated in figure 6.2. Calculate the wavelength of the light emitted by the laser. Okay, so first of all, the formula. The formula is wavelength equals AX divided by D. And can someone tell me the values? What's A, what's X, and what's T here in this formula? Anyone who has any idea what these A, X, and D are? Yes, A is slit spacing, which is the distance between the two slits. This is A, and D would be the slit to screen distance. So this is D, and what would be X? X would be the fringe separation. X would be the fringe separation, meaning this separation between any two adjacent fringes. Like they could either be dark fringes or bright fringes, not a concern, but as long as they're fringes, it's right. So this is the formula, and this is X. So they've told me the slit spacing. Okay, so I need to find the wavelength. I know the slit spacing. The separation of slits is 0.48 millimeters. So times 10 to the power -3. This is the separation of the slits time X. So what would be X? I know that these are 16 fringes and this whole length is 36 millimeters. So I could just do 36 times 10 to the power -3 to convert it into meters divided by 16. So this would give me the value of each fringe, the, the distance between two adjacent fringes, and then D. So D is 2.4. And can anyone tell me the answer? Like what would be the wavelength that I'll get? Okay, so maybe you all can do it yourselves. Like this is how we'll do it, and maybe just do it whenever you get time. Okay, so moving on with this question. Okay, so yeah, this question is done. Is it? Okay, so the next part. Uh, by the way, just give me a minute and then I'll proceed. Okay, so actually my guess was correct. There is some there is a part missing from this question, and just give me a minute. I'll dash that part as well. Okay, so this was the next part of this, and I've often found students having some confusion at this. Okay, so like maybe pay attention to this. I hope this comes clear to you this time. Two dippers, D1 and D2, are used to produce identical waves on the surface of water, as illustrated in Figure 6.3. Point P is 7.2 centimeters from D1 and 11.2 centimeters from D2. The wavelength of the wave is 1.6 centimeters. The phase difference between the wave produced at D1 and D2 is 0. Set and explain what is observed at P. We need to explain our observation at B. So now the thing is that this is 7.2 centimeters and the wavelength of the wave is 1.6 centimeters. So if I divide 7.2 by 1.6, 7.2 by 1.6, I get 4.5. And that would be the number of waves, like one wave, two wave, three wave, four wave, and like 4.5 waves. That would tell me the number of waves they would be between point 1 and point 2. Like point D1 and point P. So that would tell me the number of waves. I just randomly draw and I hope these are equal to 4. Let me draw this correctly. One wave, two wave, three wave, four wave, 4.5. Yeah. So these would be one, I don't know if these are three waves or 3.5 or 4.5 waves, but there would be some waves like this. And then there's this another part which would be 11.2. So if I divide it by 1.6, I'll get 7. So which means that there are 7 waves produced between this whole thing till it comes to point P. So 7 complete waves and 4.5 complete waves. So this is 4.5 and 7.7 lambda. So 7 waves would travel till they reach point P from D2, and 4.5 waves would travel till they reach point P from D1. So the next thing I do is I know that the waves when they were produced had a phase difference of 0. So when they were initially produced, they were produced just in line. So when they arrive at point P, their path difference, so their path difference, I can find simply as uh, 7. Just I could simply find it as 7 minus 4.5. So I'll get 2.5 lambda. So 2.5 lambda would be the path difference between these two waves. And we obviously know whenever the path difference is in 0.5s, or this path wave could alternatively be written as a phase difference of 180 degrees. So whenever the phase difference is 180 degrees, the waves destructively superimpose and we experience a point where there's no wave. So what's observed at point P, we observe at point P that there is no movement of water because the waves constructively interfered with each other. So that would be my observation at point P initially. The next part is set and explain the effect on the answer to C1 if the apparatus is changed so that separately meaning the assumption in part one is different, is independently applies, and the assumption in part two, they both are mutually exclusive events. Like they don't affect each other. We're not doing applying both changes at the same time. We just apply change one, and then we come back to what it was, and then we apply change two. So if the phase difference between the waves at D1 and D2 was 180 degrees in the beginning, so if the difference was initially 180 degrees, the initial part difference was already phase difference was already 180 degrees, and so would be the part difference. So the waves as they would travel, they would always be lambda apart. So an example of this could be if both waves were traveling in the same direction. Just a second. So if these are my waves, what could be the case is if both waves had the same path difference or a path difference of 0, they would have traveled in space just like this. They would have been at exactly the same points. Okay, so they would have had exactly the same point. But if the path difference is lambda, meaning that both waves would be a path difference apart. So obviously, if they meet at point P, where one wave has traveled 4.5 lambda and the other wave has traveled 7.5 lambda. So there's this all difference due to the travel of 2.5 lambda. And then there was an initial difference as well, which was 0.5 lambda. So the total path difference becomes 3 wavelengths. So the initial path wave is 3 wavelengths, which is can also be written as 360 degrees, a phase difference of 360 degrees. So whenever there is a phase difference of 360 or 0 degrees, so the waves constructively interfere, and we see a wave of an amplitude which is larger than the original amplitudes of wave D1 and the wave coming from D1 and D2. Yeah, so someone just messaged me that it's kind of confusing, but as long as you're understanding it, what's happening, it's good. A confusion could be like it's complicated. That's good because a question is a bit complicated, and I don't know. Like I've had many students ask me the same question again and again. I've taught them as well, and then they ask the same question again and again because it is a bit confusing. So as long as it's only complicated, it's good. But if you're not understanding, then please ask, and that then there's a problem. But if you're understanding it but you're finding it complicated, no issues with it. Okay, so the next part is intensity of the wave from D1 is less than the intensity of that from D2. Okay, so and part difference is still zero. This assumption does not apply to part two. Okay, so someone was asking me to explain this again. So okay, so I will explain this again, but let me just complete part two. Okay, so now the intensity of the wave from D1 is less than the intensity of the wave from D2. So the both waves have different intensities. Now what happens is when two waves superimpose with each other, what was happening was waves were destructively interfering initially at this point. They were destructively interfering. And now, yeah, someone asked me about the recordings. They will be uploaded on YouTube. So I'll share the link. Okay, so when waves were constructively interfering, for there to be constructive interference, they were like something like this. So their amplitudes added up, and I got a straight line like this. So this was the resultant line. This was D1, let's say, and this was D2, let's say. So this was my resultant line. But what happens is if the intensity of D1 is less than D2. So my wave D2 was something again like this. But the intensity of D1 decreases. It becomes something like this. The waves would still destructively interfere at these points, and the amplitude would subtract. But it would no longer be a straight line. It would be a wave with reduced amplitude like this. A wave with a reduced amplitude. So if the intensity of D1 is less than the intensity of that from D2, so we would still observe a wave, but the amplitude of this wave would be very less than the amplitude of either of the waves which are coming from D1 and D2. So is this part clear to everyone? Do let me know because this question is important. So if anyone who's having any confusion, like just let me know and I'll be more than happy to explain it again. So the second part, I'll come back to the first part after this again. Okay, so if no one's like telling me it's no one's telling me it's confusing or like I'm assuming it's clear to everyone. Okay, so the first part was I have a wave which is like this. These are what four waves, and this is like the fifth wave. So this is basically 4.5 wavelengths. 4.5 wavelengths. Okay, so the next part was the other wave was 7 wavelengths. So if I have another wave which is coming from a point like this, okay, so these are 7 waves, and that is a single wave. Or just a second. So these are 7 waves, and they're traveling and meeting at a point here. So assume this to be point P, and assume this to be point D. What's the point? D2, and assume this to be point D1. So this is what was initially happening. So these were 7 wavelengths, 7 lambda, and that was 4.5 lambda. So when they were intersecting or like combining, superimposing with each other at point P, so they were constructively interfering because both waves were in line with each other. So at P, I realized that the amplitude is way greater than what the initial amplitudes of the wave would have been. So I hope this is clear to everyone. Now what happens is I change the phase difference. So when these waves, if you see, when these waves were initially made, so they had a part difference of zero because this point and this point, they don't have any part difference. The part difference between these points is zero. So what do I do now? I make the part difference to be equal to what? I make the part difference to be equal to uh, half a wavelength, meaning that these points are something like this. Just a second, let me first copy this somewhere. So this was the initial case. And this time, what happens is the phase difference between these is reduced. So I start these wave with the initial part difference of half wavelength, meaning that when they intersect with each other, they're having a part difference. This is still seven waves. It's still seven waves from D2, and it's still four waves from D1. And when they're intersecting, if you see, this is just the path after the a trough, and for the upper wave, this is just the path after the trough crest, and this is just the path after the trough. So these points, this point on like this point and this point, what's the part difference between these 2 points? So you can like maybe take a screenshot and observe this in detail after the class, and you'll realize that the part difference between these 2 points, I'll call them point A and B. The part difference between these 2 points happens to be equal to 180 degree, half wavelength or 180 degrees. So that would be the part difference, and that's why when the waves intersect at that point, they destructively interfere, and there is no amplitude. So I hope this part became clear to you guys this time. Okay, and as for the second part, the second part was then when waves superimpose destructive interference, the waves are in exactly the opposite direction, right? The waves are like this. So what happens is their amplitudes add up, which basically cancel out, and we get a straight line like this. So the amplitude of A, let's call it A1, and let's call this the amplitude of A2. So what was happening was A1 plus A2 was equal to 0. So that's why we got a line with amplitude 0. But and for that, obviously, A1 was supposed to be negative A2. So both were supposed to have the same magnitude and the negative signs. But what happens is we decrease the intensity of a wave, and therefore its amplitude, and the amplitudes weren't the same. So if A1, let's say, was less than A2, so obviously now in this case the waves could not destructively interfere. They would interfere in the same way, but when they would interfere with each other, the resultant of these waves wouldn't be a yellow straight line. The resultant would again be, if I add these amplitudes, would be a line like this. This blue line would be the resultant. So I wouldn't see no wave. I would see a wave with a very less amplitude. So that's what I would see. So I hope this part this time is clear to everyone. Okay, so there's one more question for today, and uh, that'll like be the last question we'll do today. So state the principle of superposition. So superposition is the principle, like it's a 2 mark question. So there should be two key points. The one key point would be when two waves meet at a point, and they superimpose. Obviously, for superposition, the points should meet at a point. So when a wave traveling, when two waves are traveling and they meet at a point, the resultant amplitude of both the waves is equal to the algebraic sum of both of their uh, of the amplitudes of both the waves. So the resultant displacement is the algebraic sum of their respective displacements. That's the principle of superposition. And now the next part is state what is meant by coherent waves. So coherent waves are waves which have a constant phase difference, and obviously for that the frequency is also supposed to be constant. So if it's a 1 mark question, so just tell them that a constant phase difference would suffice. If there's a constant phase difference. But if it's a 2 mark question, then also go ahead and tell them that the phase difference would be the same, so would be the frequency. Because if the frequency is the same, it's not the same, it's not possible for the phase difference to remain the same beyond an instant. Set the phase difference between the waves meeting at Q. Q is what? B is a bright fringe. T would be a dark fringe. Q would be a bright fringe. So obviously they're now asking me to tell the phase difference between waves meeting at point Q. Q is a bright fringe, meaning the waves are constructively interfering. So if the waves are constructively interfering, the phase difference would either be 0, would either be 360, would either be 720, and so on. So you could write any of the answer. You could write 0, you could write 360, you could write 720. All of those would be correct. But the better answer right now here would be 360, because that's how we work. Because that's how it works. This is all these points are bright points. All these bright points have constructive interferences, but the actual phase difference here is 0. For the second fringe is 360, for the third fringe it's 720, and as we move on we keep adding 360. So whenever we move a bright fringe above or beneath the central bright fringe, we add a phase difference of 360. So the actual answer could be 360, but even if you write 0 degrees, it would still be correct. And then find the part difference in nanometers of the wave meeting at point P. So the waves meeting at point P. So obviously, if point Q is 360, this is 360, and this is 720. So point D is exactly in between both these points. So it would obviously be what? 720. It would exactly be half of it. So this would be 540. So the part difference, a phase difference would be phase difference would be 540 degrees, and a phase difference of 540 degrees would be equal to a part difference of I think 1.5 wavelengths. Yeah, one, because 1 lambda equals 360 degrees. So if it's 540 degrees, it's equal to 1.5 lambda. And I know that the wavelength of the wave is 610 nanometers. So 610 times 1.5 will give me the answer. 1.5 times 610. This would give me 915 nanometers. So 915 nanometers would be my answer. The next part would be determine the distance A between the two slits. So I now need to find the distance A between the two slits. And the formula is, of course, wavelength equals, just a second, wavelength equals AX over D. And they're asking me to find the distance A between the two slits. So for that, I know the wavelength? Yes, I know the wavelength. It's equal to 610. And then there's A, which I don't know. Then there's this distance between the screen, which is 2.7. And then I need to find the distance between two adjacent fringes. So what would be the distance between any two adjacent fringes? I just need to find that and tell that to them. So how would I do this, or how would I find this distance? The way would be similar to how we did before. So this is 22 millimeter, and these are what? 1, 2, 3, 4, 5. So these are 5 actual fringes. But if I like ask about the difference, so if I need to find the difference between any two fringes, so I would just simply divide it by 22 divided by 4. So this would give me 22 divided by 4. This would give me 5.5 millimeters. Let me just remove this all so I could make this part clear. So if I divide this by 4, I'll get the difference. So this would be 5.5, and this would again be 5.5. This would again be 5.5, and this would again be 5.5. This is how I got 22. So that's why I divided it by 4, and I got 5.5. So that's what I write, times 5.5, and it's millimeters, so I converted into meters, and 10 to the power negative 3. So with this, I just get simply my answer, and that's all you write. So next part, a higher frequency of visible light is now used. State and explain the change to the separation of the fringes. So if I use a frequency, light of higher frequency, so a higher frequency would mean that the wavelength would be lesser. Now the wavelength is less, but A is constant, so is D. What would happen to X? X would reduce, so the separation would also decrease. So that would be my answer. And now the next part is the intensity of the light incident on the double slit is now increased without altering the frequency. If the frequency has not been altered, the position of these bright and dark fringes would not be altered, would not change, because everything has remained the same. This was my formula, ax over d, and everything remains the same. There is no amplitude in this formula. So if I change the amplitude, nothing in this formula would alter. So I just changed the amplitude, and now they're asking me to compare the appearance of fringes after this change, after this change with their appearance before this change. So how would this change affect the appearance of fringes before and after? So if the amplitude is increased, we know that dark fringes were points where there were destructive interference occurring. So obviously there was no amplitude, so there would be nothing. But the bright fringes were the points where there was constructive interference. So the amplitudes were adding up and like doubling. So the amplitude at a bright fringe was 2 times the amplitude of the wave, of the actual light which was being passed through the double slit. So if I increase this amplitude A, so so obviously the value at the bright fringe would be twice this increased value. So the bright fringes would be more brighter, but the dark fringes would be the same. So that would be my observation. And yeah, so and the spacing would be the same. So the spacing and everything remains the same, except the fact that the bright fringes are more brighter and the dark fringes are dark, because there is no light there. So you can't make them any more darker because they were already at 0. So you can't go negative, obviously. Okay, so this is how we answer this. And with this, we'll end the class of today. So if anyone has any questions regarding what we've done, any confusions, feel free to ask. If not, then we'll just end for today. You're welcome. Okay, so if anyone has any confusions, feel free to ask. There's no problem. Otherwise, I'll end the class. Okay, so I'm assuming no one has any questions. Okay, so then let's end, and hopefully we'll meet tomorrow, inshallah. Assalamu alaikum.